Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to explain why it's possible to avoid the concept of resonance by using molecular orbital theory. So in order to answer this question, we need to go back to our valence bond theory and resonance structures. So using as an example NO2 minus, when you're using Lewis dot structures and valence bond theory to show that there's resonance in your molecule, you wrote these Lewis dot structures, and the resonance came in because here you have a double bond between the oxygen, but because the electrons are delocalized, you can push the electrons here, right? So one of these lone pairs can then form a double bond here. That would then give the nitrogen a 5 bonds or an expanded octet, which is not possible for nitrogen because it's in period 2 on the periodic table. And if you remember, expanded octets can only happen for elements that are in period 3 and lower, or lower in the periodic table. And so in that case, the electrons in the double bond here would be pushed onto this oxygen, and then you get 3 lone pairs on the oxygen here, and you get a double bond with 2 lone pairs here, and then you get the resonance structures, and you have this arrow. Oops, I forgot my negative sign there. And so in order to explain what the molecule is, then you have to draw these resonance structures. And of course, the idea here is not that you have a fluctuation of the molecule between these two possibilities. It's not like the molecule of NO2 minus is in this form, and then it switches this form, and then it switches this form. That is not the idea here. It's that the actual molecule is some hybrid of these two, and then you could figure out what the bond order is by taking the number of bonds and then dividing by the number of atoms that are bonded to the central atom. So you would figure out the bond order by saying, okay, you got 3 bonds, but you got 2 atoms that are sharing those bonds. So then to find the bond order, you would then take the 3 bonds, divide that by the 2 atoms. So you're dividing the 3 bonds equally among the 2 atoms, and that means you get 1.5 bonds shared here. So the bond order between both atoms are going to be equal, and they're both 1.5 bonds, right? So that is how you can use valence bond theory. But molecular bond theory, or molecular orbital theory, I should say, avoids the whole idea of resonance by using molecular orbitals. Okay, so going back to molecular orbital theory, remember you can use a sigma bond format or structure here to explain the sigma bonding, right? So here we know that NO2 minus has a trigonal planar structure. The bond angles are close to 120 degrees, so that indicates that there's sp2 hybridization. So you can use the hybridization model to kind of explain the sigma bonding, right? So here we have sp2 hybridized oxygen, sp2 hybridized nitrogen, and sp2 hybridized oxygen. So you fill in the electrons. So you have 2 lone pairs here. You have a sigma bond here. So 1 electron from this sp2 hybridized bond, 1 electron from here. They're going to pair up. You've got a lone pair on the nitrogen. You've got a sigma bond here between this oxygen and nitrogen. And then you've got the 2 lone pairs here. If you count out the number of electrons used here, it's 14. So we got 2, 4, 6, 8, 10, 12, 14. So we used 14 valence electrons, but the total number of valence electrons is 18. How did I get 18? Well, nitrogen is in group 5, that's 5 valence electrons, plus each oxygen is in group 6, that's 6 valence electrons. I have 2 oxygens, 6 times 2 is 12, so that's going to add 12, plus I have a negative 1. That means I have an extra electron, so I have to add 1 to my total, and I add that up, I get 18 total valence electrons. I used 14 so far in my sigma bonding structure here. That means I have 4 left. So 4 electrons are left over. Now, oops, I made a mistake. Sorry. Let's see. Yes. So you'll see here, I didn't make a mistake. So sorry about that. So you'll see here, all of this is sp2 hybridized, which means that each of the oxygens and the nitrogen have 1 unhybridized p orbital. So that gives us 3 unhybridized p orbital. And again, according to molecular orbital theory, those p orbitals each will contain an electron, right? So 1 electron in each of the p orbitals, that's 3 electrons, plus the 1 electron left over from the charge. That's 4 electrons, 3 p orbitals, each contains 1 electron. And so that allows for the interaction of the unhybridized p orbitals. So those p orbitals can then combine to form molecular orbitals. Remember, the number of orbitals, the number of molecular orbitals that you get out is the same as the number of atomic orbitals that you put in. So since each atom has an unhybridized p orbital, then they can combine to form 3 molecular orbitals, and here they are. If you want to see what the molecular orbitals look like, I have a video in which I went over this molecule and I drew the molecular orbitals. This had to do with molecular orbital theory and multiple bonds. So go to my video on molecular multiple bonds using molecular orbital theory or MO theory. You'll see the pictures there. But these are the molecular orbitals. This is a bonding molecular orbital. It's a pi bonding molecular orbital. This is a non-bonding molecular orbital, and then we have a pi star or pi star anti-bonding molecular orbital. So the star refers to anti-bonding. If there is no star, it's bonding, and of course NB is non-bonding. So this is the order of the molecular orbitals. We have 4 electrons. We could fill in the molecular orbitals with the electrons. So 2 in the bonding molecular orbital and then 2 in the non-bonding molecular orbital, and I have no more electrons to put in, so the pi star anti-bonding molecular orbital is empty. So now I can calculate the bond order from the molecular orbitals. So remember, calculating molecular bond theory, or the bond order using molecular bond theory, says that it's the number of bonding electrons, that's the number of electrons in bonding orbitals, minus the number of electrons in antibonding molecular orbitals or antibonding electrons. So this is a bonding molecular orbital, so I have 2 electrons in there. This is a non-bonding molecular orbital, so non-bonding molecular orbitals are not bonding molecular orbitals, so those do not count. So we ignore those. So I have 2 bonding molecular, or I have 2 bonding electrons. So I don't have any anti-bonding electrons, so that's 0. And then you take the difference and divide that difference by 2. So since 2 minus 0 is 2, that's 2 divided by 2, and that gives me 1 pi orbital, pi bond. So I get 1 pi bond from the molecular orbitals involving the unhybridized p orbital. So we've already got our sigma bond, right? So we already got the sigma bond from this here, right? We could have shown the sigma bonding as well in our molecular orbital, but we're ignoring that and only focusing on the molecular orbitals that come from the unhybridized p orbitals. Okay, so now that we know that we have one pi bond, that pi bond, the electrons are delocalized. That pi bond is delocalized. So that pi bond is going to be shared between the atoms. So again, since I have one pi bond, that's going to be divided equally among the atoms. So I have a bond here and I have a bond here. So that is going to be divided by 2. So it's going to be split between here and here. So that's a half of a pi bond. You'll notice that I have a sigma bond here and a sigma bond here already. So it's going to be a full sigma bond plus half of a pi bond. So the bond order for the total bond order is going to be 1.5. So if I divide this by 2, right, this one pi bond is divided by 2 among them. So then again, the bond order, the total bond order is going to be equal to 1 sigma bond plus a half of a pi. So that's 1.5, just like we saw over here using valence bond theory. But we avoided the whole issue of resonance structure. We didn't have to refer to our resonance structures or resonance at all because we have molecular bond theory, molecular orbital energy diagram in which we can calculate the bond order directly from the molecular orbitals. And that is how it is possible to avoid the whole concept of resonance by using molecular orbital theory. I hope this was helpful and insightful, and I hope you learned. If you did, if it was interesting, then by all means, like the video, share it, hit that like button somewhere over here, I think. Look for it, you'll find it, I believe in you. Also, do me a favor, help me out, subscribe to my channel, hit that notification bell. When you do, click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, put that down below. If you have a topic you would like me to put that down below. I would be happy to do that for you. Thanks for joining me and have a great day.